Okay, so today we're looking at rotational motion. Now we've been talking about, all right, we've looked at momentum. Last chapter was what? It was, well, good heavens, I just went completely blank. Angular velocity, angular acceleration, and moment of inertia. Now remember, that is only for objects that are in rotation. We have not applied the force yet to cause rotation. Now we are, okay? And I don't know if you consider this, you think, well, if I apply a force, that's really the only thing that's producing motion. No, it's not. You got to realize, once you begin motion, that's why we have moment of inertia. Have you ever thought about why is it hard to stop something that's really large, especially if it's rotating, since we're talking about rotation? If you've ever thought about why is it so hard to stop, say, a big flywheel on a machine, okay? Well, once you get it started, its own momentum and its own moment will help keep it going, okay? But you got to realize, you've got to stop that. If you want the machine to stop braking, you want to brake, put a brake on it and slow it down or stop it, then you've got to basically apply a force in the opposite direction, and you have to take into account the moment of the device. And that's where our different sizes come in, and also the axis of rotation. Remember, we had, 9 different scenarios, different types of materials, that the moment of inertia all depended on the type of material and where the axis of rotation was. So not only are forces involved, but you can't forget about the moment too, okay? I don't know if you've ever been around large equipment. I know old tractors. I like old tractors. My grandfather has a 420 John Deere, the old Poppin' Johnny, and I loved old John Deere tractors. If I was rich, that's what I'd do. I'd just play golf, fish, and hunt, and work on old tractors and cars and stuff, because I like that kind of stuff. But I was at gas station a couple months ago, and a guy pulled up in a 1940 John Deere Model A, and it was in really good shape. It had power steering. I couldn't believe this. Had hydraulics and everything, and those were big tractors. And they had the big flywheel on the side. They still had the flywheel on the side. And those tractors would literally probably pull a house because they created so much torque. They were only 2-cylinder engines, but they had a real long stroke. And so that long stroke helped produce a lot of power. And then that big flywheel, once you get that big flywheel to spinning, you produce a lot of torque, okay? So you have to look at the moment of inertia of the device, and then, of course, the force applied, or what we call torque, okay? Now, if any of you have ever used a lever, a wrench, most of you should have, you jack up your car, okay? You are actually creating torque, okay? When you jack something up, when you put that handle in the jack, if it's an old, what I call not the hydraulic jacks, but that will ratchet, what do you call that? Gosh, I'm blank. I call it a ratchet jack. Anyway, but where you crawl up the teeth with using the lever. Those are the old jacks. Most cars now don't have those. They got a hydraulic jack or a screw jack. Most of them now when you buy a car, but used to, that's all cars had, was those bumper jacks. Yeah, it's like a ratchet as you go up. They were dangerous as forked lightning too. They were really dangerous, because when you went to let that baby down, if you weren't careful, if you didn't work that lever right, it would all the way down there, or just completely fall and break a foot or fall on something you didn't want it to fall on. They were very dangerous. I hated those things. Okay, so I said all that to say this. Torque creates motion. So how do we define torque? Okay, torque defined, oh, come on. Torque defined, okay, it is the tendency of an outside force to start or stop motion. And it's usually what type of motion? Rotational motion. Okay. Rotational motion. Okay. So you have torque converters on a car. Why does the crankshaft not go straight into the transmission? Well, good grief, you put it in gear and you'd strip the thing out. There's no pause. In other words, you want to build up, you want it to build up, not be instantaneous. And so they put torque converters on a transmission so that the torque created by the rotating crankshaft, once it builds up enough torque, it begins to turn the transmission slowly. Now, there are, it all depends on how much power you apply to the engine, of course. You can start real fast or start real slow. You get into racing, they have things called stall converters, if you know anything about racing. Once it hits a certain number of RPMs, it goes into gear, and buddy, you get a quick jump off the line. That's why they use them, okay? But torque causes rotational motion. So if you think about swinging a golf club, you're creating torque, okay? You create torque. Swinging a baseball bat, that's torque. What's another good example? Using the lever jack, that's torque, okay? Oh, Lord, there's lots of applications. Electric motors, when they begin to spin, okay? When they begin to turn, or they turn a pulley or a flywheel, that's creating torque, okay? And torque, as you'll find out in next semester when we look at amperage, why do large motors have to have high amperages? Well, because they have to create a lot of torque to cause the object to turn, okay? And so we look at the relationship of torque and amperage, okay? So torque is one of those things that we use all the time and we kind of forget about it being there, but it's extremely important because without it, y'all, it's hard to create motion, okay? And so we have the moment of the device, but we also have the torque. Now, very important you understand that the direction of the applied force is everything, okay? For example, and also where you apply the force, okay? And they show you here, well, if I grab the wrench up here, I'm not going to get much done, am I? It's bugged the fire out of me to see someone take a claw hammer, okay, and grab it way up here at the head and go peck, 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 peck like a woodpecker. I just want to take the thing and sling it and say, get out of here. I'm tired of fooling with you. I'm old school carpenter. You got to realize, you grew up with my dad, you did it right. And if you didn't do it right, you learned how to do it right. And if you couldn't learn how to do it right, then I guess you had to go do something else. Huh. Yeah. So, he was a stickler about, doing things right and about using your head. If I ever heard him say think once, I heard him say it 1,000,000 times. And I say that in teaching all the time. Well, now think about it. Where did I get that? I get it from my dad. Be analytical. So what do? You grab that hammer down towards the end of the handle. So why? Because you create a lot of torque, okay? You create a whole lot more torque, you don't have to do near as much work, okay? A lot more torque makes the job much easier. He could drive a 16-penny nail with one lick. He's a man, I'm telling you right now. I watched him do it many times. He'd set it, and that was with a 12-ounce hammer. That was with a 12-ounce hammer. Why he used a 12-ounce hammer, a finishing hammer, I guess because when he got to do the trim and stuff, he thought, well, I won't be as prone to, what we call moon it up, leave hammer tracks. Donkey tracks, yeah, donkey tracks, that's a good one. We'd say moon it. Boy, he mooned that piece, didn't you? All right. But he could drive a 16-penny nail with one lick. He could set it, and soak that baby, and it was gone. And a 16-ounce hammer, which he rarely ever used, he definitely could. Now, I never was that good. But my dad could create a lot of torque with that claw hammer. And he created a lot of torque with that belt, too. Or rope or whip or whatever it was we got. Whip. I didn't get many, but I didn't forget the ones I did get. So back in the day, all right, when parents still discipline kids. So anyway, today I think it's about obsolete. I almost want to, well, anyway, I got to get off that. All right, get off the soapbox. Okay. So torque creates motion or stops motion. Okay. And so please understand, and where we apply the force. So we get into this next slide, and I wanted to keep this slide in here. So the line of action, okay, the line of action. That is the line at which we apply the force. Okay, so if I'm going to pick the table up, okay, all right, if I'm going to pick the table up, I pick straight up, my line of action is this way. It's 90 degrees to the point of rotation, okay? It's 90 degrees. However, if I try to stand back here at an angle and pick it up, oh, it's a lot harder, isn't it? Okay? A whole lot harder. Well, why? Because I wasn't at 90 degrees. We know the sine of 90 is 1, isn't it? Okay? It's a good example. If I stand here and kind of lean back and pick it up that way, it's a lot more difficult. If I stand right over it, pick it straight up, it's pretty easy. Okay? So the line of action, the angle between the line of action and the point of the lever arm is very important. Okay, and I'm telling you, if you and you're engineers, many of you are going to be engineers. Y'all are going to be using your hands a lot. More than likely, you're not always going to be at a desk working on a computer, writing a program or doing a bunch of calculations. You'll do some of that, but I guarantee if you work at the arsenal, you work government. My nephew, he's climbing those towers all the time. Radar tower. That's what he does. He repairs and builds radars. The company he works for, and they do a lot of subcontracting for the government, for the Air Force. And he said, man, it's amazing. He said, what the task we're given. Where they put this brand new radar technology on towers that are 30, 40 years old, and he said it's tough because we can't tear the tower down and build a tower that would really be feasible for it. We have to make the one we have work. And he said, boy, he said, I don't use a lot of my engineering like I thought I would, but he said, I do use a lot of my physics, the concepts of physics. And two, he said, a lot of it's trial and error. He said, we'll try this and then we'll adjust it. So he said, for me to tell y'all, don't expect to use a lot of your engineering coursework in your actual job. That's just the way the cookie crumbles. Depends on, I guess, what you're doing. But I guess if you were, doing the drawings and stuff, you would still. But anyway, but yeah, your concept of physics is important. Like he told me building the radar tower, you got to remember your laws of electromagnetism, because the steel structure of that tower is going to scatter that signal, interfere with that signal. So you got to fix that tower so it won't do that, and you won't get crazy readings on your radar. So stuff like that. Okay. All right. So back to application here of torque. I said all that to say this: your line of action and your lever arm. So if you have a 90-degree angle with the lever arm, then you're applying maximum torque. Will you always be able to apply maximum torque? Well, it all depends on the need. You may not need to, okay? Or you may not be able to, okay? You may not be able to. All right, so here you see the drawing, the line of action. Here's our lever arm, okay? Line of action, 90 degrees, you get maximum torque. Notice right here, the line of action is what? Your line of action's this way. Well, here's your lever arm. Do you think anything's going to happen here? Nope, it's not going to move. Zero torque. All right, and so now let's get into how we actually calculate it. I'll give you three equations here to calculate torque. We can calculate, and by the way, that's the Greek letter tau. Tau. Typically we write torque, it's a backwards T. Okay? It looks like a backwards cursive T, right? Or is that a J? T. Well, that's a T. I put the little hook on the end of it. Yeah, backwards T. Yeah, I put that little hook that's going up. That's the way my physics professor did it. All right? So the Greek letter tau is for torque. So that's torque, tau. We can calculate it by applying the force times the length of the lever arm, or the radius from the point of rotation times the force applied, sine theta. Now the sine is the what? The sine is between the line of action and the lever arm. Please understand that, okay? please, 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 please make sure you understand that, okay? That the sign is between the point of action, the line of action. Where's the line of action? Line of action's here. If the line of action, all right, so if you're pulling straight up this way, then you have what? You've got an angle here, and this angle and that angle are congruent. You have an angle with the lever arm, don't you? But what if you were pulling it, let's say you've got a bolt here and you got a wrench on it, and you pulled it that way? Well, your line of action's 90 degrees. Okay, this diagram, it's showing you the line of action's this way, like that, okay? So it's not 90 degrees. In other words, he's pulling the bars at an angle, but he's pulling straight up on the end of the bar, okay? So again, you've got to orient your angle with your line of action and your actual lever arm, okay? Okay, please remember that. Now notice too, they talk about the tangent. The tangent, you can find it also by multiplying the force, the tangential force times the radius, and the radius again is what? This is the radius right here. There's the radius. You could actually say from the fulcrum or the axis or point of rotation. This is R. That right there is R, right there. Okay? Okay. Okay? So please make sure that you understand when I say radius what I'm talking about when it comes to torque. Okay? All right, any questions on that? And two, we can use some action or some symbols here to show, is the torque out of the page or is the torque into the page? Okay? Well, of this application, the torque is out of the page. In other words, the torque is coming up and hitting me in the face. And by the way, torque is also a vector. It is a vector quantity. Okay? So it's coming up and hitting me in the face. If I was pulling down on the lever arm, then the torque would be what? Into the page, and how do we represent that? Okay? We use an X. Think about shooting an arrow. Why do we use these symbols? Okay, think about shooting an arrow. If the arrow is coming towards you, it looks like a dot coming at you, doesn't it? If the arrow is going away from you, you see what on the back of the arrow? The feathers, right? What do you call that? The what? Fletching. Yeah. I couldn't. I'm not. You can tell I'm not much of a hunter. I don't bow hunt. Okay. Okay. So think about it that way. If it's going away from you, you see the fletching. All right. Okay. So what about? And I said torque is a vector. Now, all right. We've given you what? We've given you 3 ways we can calculate torque. But torque as a vector. All right, now, how do you do this? If you take your, again, right-hand rule, and you curl your fingers in the direction of what? Take your right hand in the direction of the force around the rotational axis. Okay, so if it's rotating counterclockwise, then you have what? The torque is considered to be positive. It's out of the page. Okay? All right. However, if it's counterclockwise, then it's this way. So, in a nutshell, then we can do what? Now, this takes the sign away. This is under the assumption that we're at a 90-degree angle. Okay? We're just assuming that the force applied, the line of action is 90 degrees to the lever arm. So we take the sign away. All right? Okay, so I'm not giving you really another equation. We're just assuming that it's a 90-degree angle. Okay? Okay. Any questions on that? But again, don't forget that right-hand rule. Okay? That's really important. Okay? Now, because torque leads into angular momentum, if you've ever wondered why a top will spin straight up. Okay, well, it all depends. It all has to do with how the torque is applied. You ever noticed you pull the string horizontally? When you pull a top, you pull it horizontally, don't you? But the top stands straight up. Well, which way is your angular velocity? Well, your angular velocity is what? This way, isn't it? And I'm getting a little ahead of myself. Well, guess what? Your torque is what? And your angular momentum is, so it makes the top stand up. Okay, that's why a top will stand up momentarily. We know gravity and friction eventually slows it down and it collapses. I mean, that's why. We know that's why. But initially, it'll stand up. Okay? All right? Okay. All right, I'm getting a little ahead of myself. I don't know if we'll get to that today. We may. All right? So, torque and angular acceleration. Now, so let's tweak it a little bit. And let's look, instead of looking at just the radius and the force applied, is that the only way we can look at torque? No, it's not. Okay? Because you know you have rotational motion. And what do we have with rotational motion? Oh, by the way, I didn't talk about the units. I'll talk about them here in a second. All right, we have what? Rotational motion. We have angular velocity, and we also have angular acceleration. So, if we don't know the radii, or if we know the moment of inertia, and we know the angular acceleration, we can find torque also, and the sum of the torque. And of course, that sum meaning all torque applied, all torques applied to a device, okay? Now, in the case of the screwdriver, it'd be pretty simple. Okay, how do screwdrivers work? What is a screwdriver? What type of machine would you call it? Remember studying machines in junior high and early high school, physical science, and I think also maybe 8th grade science. According to what kind of 8th grade science you had. Been a long time. Okay. All right. You've got a what? There's two machines put together to make a screwdriver. Two simple machines. What are the two simple machines? Y'all don't remember your machines, simple machines? You got a wheel, a round handle, and what's that rod there called? An axle. So a screwdriver is a wheel and an axle, isn't it? Yeah, it's a wheel and an axle. All right, how do I increase my mechanical advantage, or do I make it easier for me to loosen a screw? Let's say I got a big old screw. Am I going to use a little rinky-dink screwdriver like that? Probably not. I'm going to use a large handled screwdriver with a large axle, right? Because a big screw is going to have a big slot or Phillips head, whichever one it is, right? So if you ever notice when you loosen large screws, you use a big screwdriver, don't you? That has a larger handle, and if you'll notice the axle of the is different. It's a bigger axle, that's why. So you have the combination of two machines, a wheel and an axle. What about a screw? You ever looked at a screw? You ever noticed how it's conical? And you ever noticed how it makes a, what do we call that? A vortex, looks like, sort of. It spirals. It spirals up the post. So you have a what? You have an axle with what wrapped around it? An inclined plane. Okay? So look at a screw next time. You've got an axle, a rod, with an inclined plane wrapped around it. Okay? Two simple machines. What are your simple machines? A wheel, an axle, an inclined plane, and a lever. What else am I leaving out? Am I leaving anything out? That should be it, right? So look at a screw. It's a rod, an axle, with an inclined plane wrapped around it. That's what a screw is. All right? Screwdriver, wheel and axle. Steering wheel. You ever noticed on a truck, a big semi, they don't have them little bitty steering wheels, do they? Mm-mm. You ever noticed a truck steering wheel? They are huge, aren't they? They're big, aren't they? Well, why do they do that? Well, because you're steering something that's what? How many pounds is a semi? 10 tons, 15 tons, 10 to 15 tons. Times 2, if it say it, that's 30,000 pounds. Let's say it's 15. 30,000 pounds. Yeah, you got power steering, but still, you have to do a lot. You have to have some help, don't you? You ever seen truck drivers that have what do you call it? The knob on it? We call it, when I was in high school, we called it the handicap knob, because the only people that could get those are people that were handicapped. You couldn't put them on a car. It's illegal. Used to, it was illegal. I don't know if it still is, but we always heard it was illegal to put those handicap knobs on your steering wheel. Now, dragsters and people that race will put them on there. Why? Because they can turn the steering wheel real quick. Okay, and that's the thing was that, you know, the reason the cops don't want you to put it on there, or the police, I shouldn't say that, put it on there, because you can maneuver a lot faster and evade the police. That's what we always heard. So, but I knew someone that had one on their hot rod and drove it around town, never got in trouble anyway, never got caught. So I don't know if that's true or not. But yeah, those big steering wheels, they'll put those knobs on them, won't they? Well, why? Because it shortens the radius at which you have to move your arm to turn that wheel. Makes it a lot easier to turn. You ever thought about that? Okay. So a steering wheel's a wheel and axle, isn't it? Sure is. Okay. All right. So you're using machines all the time, and you didn't realize it. Simple machines to make compound machines. You've got a lever. Oh, you've got the fulcrum too. I forgot about the fulcrum. Okay. You use levers all the time. Lever's a simple machine. Also, fulcrum is too. Okay. It's amazing what you can lift and move with just a lever. I did it while I was off working on a trailer. I didn't use a jack. I just got a 4x4 post and set me some blocks up and picked it up and put the wheels, tires on it and and let it back down. Real easy. I'd a whole lot rather do that than fool with a jack. I don't like jacks. They have a tendency to fall. I hate them. You know, you don't have a lot of control, I think. All right, anyway. Okay. All right, now they give you some problem-solving strategies, and I'm not going to, you don't have to write this down. This is on page, and again, y'all, this is something that you should already have down pat as far as how to solve these problems. Well, I said it was in here. Maybe they left it out of this chapter. No. Page 308. Yeah, page 308. That's where you can find these two slides, okay? All right? And so you know, doing your problem solving for torque's not any different than when we're looking at forces. Remember what I always said? You always sketch it. You draw your free body diagram and then choose your coordinate axis. Always put X and Y and then label it, okay? And then you choose your equation, okay? All right, okay? All right, I'll tell you what, it's 10 till. Let's stop there. Let's do some problems. How's that sound? We'll finish up Monday.